This presentation is about my work, PMTest, a fast and flexible testing framework for persistent memory programs. This work is in collaboration among University of Virginia, UC San Diego, Penn State, and VMware Research. First, I'd like to briefly summarize this work. The new persistent memory allows direct management of persistent data in memory and bypass the OS interactions, such as file systems. However, it is hard to guarantee cross-consistency. PMTest is a tool that detects such cross-consistency bugs and also performance bugs. PMTest is flexible, it supports different types of software systems, and it can be extended to different PM hardware platforms. PMTest is also fast. It is sometimes faster than state-of-the-art tool from Intel, PMCheck, and only incurs less than 2 times overhead in real-world applications. With PMTest, we have detected 3 new bugs in PMFS and PMDK applications. The new persistent memory is high-speed, persistent, and bi-addressable. For example, the figure shows an Intel DC persistent memory that sits on the memory bus. And the benefit of using persistent memory is the program can directly manipulate persistent data in memory without going through OS overhead, such as the file system. Then let's talk about how to integrate persistent memory into the system. Conventionally, programs need to go through the file system to manage persistent data, and the file system guarantees cross-consistency. With persistent memory, the program can directly manage persistent data. However, they need to guarantee cross-consistency themselves. We identified that supporting for persistent programming has 2 key fundamental guarantees. The first is durability guarantee, that is, writes become persistent in memory. So in this example, the processor is cache volatile, and the persistent memory is persistent. In order to have data being persistent, data needs to be explicitly flushed. The second guarantee is ordering, that ensures one write becomes persistent before another. Back to the same example, the processor writes back one chunk of data first, makes sure it's persisted, and then writes back the other chunk of data afterward. And so, the ordering between the 2 writes are guaranteed. The hardware provides the low-level primitives for cross-consistency. For example, in x86, the CLW and sFence instruction that writes back the data and guarantees the write-back is complete. In ARM, there are similar instructions, and there could also be many new academic proposals with new instruction extensions. So now let's take a look at how to use the low-level primitives. This example is a function that appends a new node to a linked list in persistent memory. First, it creates a new node, and then second, it sets the next pointer to the current head. And third, it updates the head pointer to point to the new node. And finally, use the persist barrier to ensure all the updates has been written back to memory. The example seems correct. However, line 3 and line 4 can reorder. So if the head gets persisted before the new node, and a failure happens at this point, the new node will be lost, so as the following linked list. To fix this, we need to insert a persist barrier between the 2 lines, and this way, the new node is guaranteed to be persisted in memory before the update of the head. Even if there's a failure, the linked list is still consistent. We conclude that it is hard to guarantee cross-consistency with low-level primitives. To make programming for persistent memory system easier, there have been libraries that provide, say, transactions on top of the low-level primitives. The most typical example is Intel's PMDK library, and there are also many other academic proposals with better performance and programmability. Here is an example that uses PMDK transaction to implement the same functionality. And with TXB and TXN that marks out the transaction region, all the updates within the region will become failure atomic. So first, the program creates a new node. Then before updating the head, it backs it up with txadd, and then performs the update to the head. And finally, it increments the list length because we just append a new node. However, in this example, the length is not backed up before update, so that if there's a failure, and the length may not be rolled back, so that the list is not consistent. To fix this problem, we need to call txadd on the list length before performing the update. And now we have a consistent list. So from this example, we conclude that ensuring cross-consistency is still hard, even with transactions. Since programming for cross-consistency is hard, how can we ensure cross-consistency? And the answer is we need to use a testing tool. So far, I have talked about the background and the motivation about this work. Next, I'm going to go to the requirements and the key ideas of testing cross-consistency bugs. We identified that there are two major requirements for the tool. First, it needs to be fast, so that we can test as many cases as possible to cover more bugs. And second, it needs to be flexible. There could be kernel modules, such as process memory optimized file systems, process memory libraries, and customized applications built on top of the libraries. And on the hardware side, there could be the existing hardware, like x86 and ARM, or academic proposals. First, I'll introduce the key ideas that makes our tool flexible. Parallel works only support specific software and hardware. However, there could be a variety of these software and hardware combinations. For example, a program can be built on top of the PMDK library and execute on top of x86 platform. It could also be a program built on top of Mnemosiny library and run on ARM processor. It can also be a kernel module that uses low-level primitives. So the question is how to support different hardware platforms and the corresponding software. We observe that even though there exist variations, the operations that maintain cross-consistency are similar. They all guarantee ordering and durability. So if the tool can test these two fundamental guarantees, it can cover all these variations. Next, I will talk about the key idea that makes our tool fast. Parallel work uses exhaustive testing. Given a trace, it permutes all possible reorderings and checks whether each of the cases is recoverable or not after failure. If the trace is length of n, then there will be n factorial cases, which is extremely slow to test every single one of them. And what we design is to test at runtime. So given a trace, we can directly tell whether or not it is recoverable without permuting all the possibilities. And our solution is to infer the persistence interval from the persistent memory operation trace, which is the interval in which a write can possibly become persistent. And given a trace, we draw the timeline. So first comes write A, and then write back of A and an S fence. So here I'm showing the persistence interval of the write A, and then follows write B in the same way. So A is always persisted before B. And another example, we have write A, write B, and write back of A fence, then the other write back to B. So here we have an interleaving interval, which means that A is not always persisted before B because of the interleavings. And based on the persistent intervals, we can let programmers ask questions such as, does A persist before B? And then check whether the program meets our requirements of cross-consistency. And now the question is, how can we let the programmers ask such questions? So next, I'm going to talk about our interface. At a high level, PMTest consists of two parts, the offline annotation part and the online testing part. And the software interface will be used during annotation. PMTest provides two types of interface. The first type targets expert programmers to provide a surgeon-like low-level interface and check the behavior against the specification. And we also target normal programmers by providing a high-level interface to minimize programmers' effort. And such interface can automatically inject low-level checkers to minimize their effort. And again, the PMTest interface is hardware independent because we capture the fundamental guarantees of ordering and durability. The low-level interface has two types of checkers. The first one is ordered before that checks whether location A is persisted before another location B. And the other checker is persisted that checks whether location A has been written back at a certain point of the program. The low-level interface can help expert programmers to check whether the implementation meets the specification for, say, programs or kernel modules based on low-level primitives and also libraries. So here is an example of using the low-level interface. First, the program injects an is ordered before to check whether the count is persisted before the hash map, which is a variable inside hash map rebuild. And the other is to check whether the hash map is persisted after rebuilding. And further, the low-level checkers can enable us to build high-level checkers for automated testing. So now let's look at the high-level interface. We currently provide high-level checkers for PMDK transactions and automatically detects cross-consistency bugs. In this example, we place a TX checker start and a TX checker end around the transaction, which is marked by TXB and TXEnd. And within this marked region, we automatically check whether there's a backup before the update. And in the end, we check whether all the updates has been persisted. And automatically detect performance bugs, such as redundant locks or backups, and duplicated writebacks or flush operations. The high-level checker, as we can see in the example, can minimize program's effort because it doesn't really require much knowledge about the program. And now let's go to the mechanism. The mechanism enables the online testing that checks against the rules and provides the testing results. The runtime checking mechanism is the following. Given a program with annotations, at runtime, it provides a trace to PMTest, and based on the high-level checkers, PMTest inject low-level checkers automatically. And the checking engine tells the correctness. And in the design of checking engine, we answer 3 questions. First is, what is the efficient algorithm for checking? And second, how can we implement this algorithm? And finally, how can we integrate this to a real system? The checking engine algorithm, as I introduced earlier, infers a persistent interval in which a write can become persistent. And in this example, write A starts an interval for A, and then CLWA is issued. Because there's no S-fence after CLWA, the write to A is not guaranteed to be persistent. And then write B comes, and finally another S-fence is issued that's guaranteed A to be written back. Then the checking engine checks first, is A ordered before B? The answer is no, because A and B can be written back at any time during these interleaved intervals. And second, it answers whether B is persisted in the end. The answer is also no, because as the F-fence does not guarantee the write back of B, because B does not have the CLW to that. The next question is, how can we implement the checking engine efficiently? For example, the program can execute a series of independent traces. To speed up the checking, PMTest checks them in parallel with multiple checking engine workers. So worker 1 first checks a trace of transaction 1. While it is still in progress, worker 2 can check the trace for transaction 2. And now worker 1 has completed the checking of trace 1, so it can take trace 3. And finally, I'll talk about the system integration. For user-space programs, we let PMTest run together with the program in the same process, so we can use a shared memory to pass the traces. However, such mechanism does not work for kernel modules, so alternatively, we use a kernel FIFO to pass the trace to the user space PMTest. And our implementation can efficiently test both user space programs and kernel modules. And finally, I'm going to talk about the evaluation results. This is our evaluation platform. We have 2 types of workloads, some micro benchmarks from PMDK, and real-world workloads includes Intel's PM-optimized file system PMFS and 2 PM-optimized databases, Redis and Memcached. And our baseline is a no testing tool ideal case, and the other is a PM check, which checks the PMDK workloads, and Redis, which both of them are based on PMDK. The first evaluation shows the performance on micro benchmarks, where the y-axis shows the speedup of PMTest versus PMCheck. On average, PMTest is 7.1 times faster. The next evaluation shows its performance on real-world workloads with different client applications. The y-axis shows the overhead from PMTest over the baseline without any testing tool. On average, PMTest only introduces less than 2x overhead. We also tested Redis, which is a PMDK-based application, using PMCheck, and it shows a 22x slowdown. So the speedup of PMTest over PMCheck on this workload is around 10x. And finally, we evaluate the bug detection. We have validated PMTest with 42 manually crafted bugs and 3 bugs we found in the commit history of our workloads. We also found new bugs, 1 crash consistency bug in PMDK applications, 1 performance bug in PMFS, and 1 performance bug in another PMDK application. And here's a bug fix from Intel. In conclusion, the new persistent memory technology allows direct management of persistent data in memory for better performance. However, it is really hard to guarantee crash consistency. PMTest is a tool that detects such crash consistency bugs and also performs bugs. PMTest is fast and flexible, it supports different types of software systems, and it can be extended to support future persistent memory hardware platforms. When testing real-world applications, it only incurs less than 2x overhead. PMTest has detected 3 new bugs in PMFS and PMDK applications. And we open source the code at the following link. Thank you.